Hello, my name is Jeff Squires and I'm one of the developers of the Open MPI project. This screencast is about tuning the openib BTL in the version 1.2 series of Open MPI. There are a lot of different parameters to the openib BTL, and if you didn't already know, the openib BTL is the plugin component in Open MPI that controls all the point-to-point message behavior over OpenFabrics networks. That's InfiniBand and iWarp based networks. So one quick command that can show you all the parameters is info --param space BTL space openib. Remember that the param command line parameter takes two arguments. Number one is the name, the type of the framework, which is BTL in this case. And then the second one is the actual component that you want to see, in this case, the openib. So this shows you all the BTL MCA parameters, and there's quite a lot of them. Now you might want to also try the -- parsable option, because the default output format of info is a pretty print human readable format, but there's also a -- parsable option which gives output suitable for sed, grep, awk, generally machine readable kinds of things. Very good and very handy for scripting. So the question is, what do they all mean? Well, let's go through some of the more important ones. Now I do want to note that in this presentation we're going to take some abbreviations here just for space on the slides and things like that. All of the parameters that we mention are prefixed. They're prefixed with BTL underscore openib underscore, and this kind of guarantees the uniqueness of the names used for the openib BTL versus the parameter names for the rest of Open MPI. So I'm not going to show that prefix here in all of these slides. So when I say foo, I really mean BTL underscore openib underscore foo. So just note that as we go through the rest of the presentation. Now here's some of the more simple parameters in the openib BTL. The first one is max underscore BTLs, and it's an integer and it defaults to -1. And what this one controls is how many OpenFabrics devices do you want each MPI process to use. A very common configuration that many users have is that they only have one OpenFabrics device anyway, so there's only one active port. But as core counts are going up, it's going to become not uncommon to have more than one device or more than one port on each device. So the max BTLs parameter might become relevant here. You say, I've got 4 active ports there, but I only want each MPI process to use 2 of them. The MTU is basically, it's a direct correlation to the hardware. What's the maximum transfer unit that will be placed on the network wire? Now, there are hard-coded values for these, 1, 2, 3, 4, and 5, and they correspond to the values that are listed on the slide here. Most have a hardware set default that OpenMPI will obey, probably around 2K or 4K. You can certainly override this, though. You might want to experiment a little bit and see if your hardware gets a little better performance with a different MTU value. The IB service level defaults to 0 and has a direct mapping to virtual lane. This really has no relevance unless your system administrator or network administrator has set up virtual lanes and told you which to use for your MPI traffic. Now I'm going to talk a little bit about receive queues here, but it's before we do that, a little review that there's 2 kinds of receive queues. On the left I show per peer receive queues, where I have a given peer and he has 4 receive queues, 1 for each of his peers out there. So for peer 1, he's got 6 buffers available in the queue. And the yellow boxes represent buffers, and the gray boxes represent incoming messages. So for example, for peer 1, there's 6 total buffers available, and there's 1 message occupying it, meaning that there's 5 buffers available for incoming messages. Peer 2 is completely blocked due to flow control, because all 6 buffers are already consumed by 6 incoming messages. So peer 2 has to wait for this guy to actually consume some of the messages off of their queue and post some more buffers. A different form of that is on the right, the shared receive queue, where you have a bunch of buffers, but they're shared between multiple peers. So you see on the left I have 4 different queues, where on the right I have 1 queue, and all the senders can send to that 1 queue. So you actually, if you count the number of gray boxes on the left and the gray boxes on the right, they're the same number, but for example, peer 2 can continue sending because there's still more buffers available. And you can play a statistics game here. So I can post less than n by m buffers available. So if n is the number of peers and m is the number of buffers per peer in a per peer receive queue situation, you can post fewer than that in a shared receive queue, particularly if you know what the behavior is of your application and you know you'll never hit that upper limit of the shared receive queue. So let's look and see how to change these values. So in the 1.2 series, RDNum is the number of per peer received buffers. Open MPI will open up a queue, a queue pair, and put this many buffers in for each per peer queue. Now, those per peer queues are opened on an on-demand basis. So the first time you do an MPI send to a peer, that's when these buffers are allocated. It's not like when you do the initial MPI init, we allocate all buffers at the beginning of time. Now, a second parameter here is whether you want to use that shared receive queue or not. And if it's 1, then these 3 other parameters come into play here. So RDMax is the maximum number of posted receives in the queue. It's the total length of the queue. So on the previous slide, for example, you look back here and you see our total length is 6 times 3, 18 buffers posted into the shared receive queue. Or you can set max per peer. So it's the max of posted receives per peer, and it's plugged into a formula there. So I do log 2 of the number of MPI2 processes. So what's going to happen here is Open MPI will take actually whichever is greater, the RD max or the RD max per peer. And then the SD max is a primitive form of flow control when using shared receive queue. It's the maximum number of posted sends that a given sender will allow to have itself outstanding. Since with a shared receive queue, you can really not know when all the buffers have been consumed at the receiver because you have multiple senders, and unless the senders are coordinating, which they're not because that would degrade performance, there's no way to know when all the buffers have been consumed. The only thing that we can do is throttle the senders a little bit. When I've sent SD max, then wait for those to complete before I send the next bunch. Now let's talk about short eager RDMA. As I discussed in a previous screencast, we use RDMA for some short messaging because it's faster than send-receive semantics on most OpenFabrics hardware. The reason for this is that it doesn't involve the software stack on the other side. It involves just the hardware and is completely asynchronous of the main CPU and whatnot. But it quickly becomes non-scalable for reasons that you have to post explicit receive buffers for each peer that you want to be able to use short message RDMA with. So OpenMPI has 3 parameters that govern these things, but let's look here at a 50,000 foot view to see exactly what we do, and then we'll put names with those parameters. So let's say we have a given receiver here, and we have 3 parameters on the left, and I'll talk about these 3 parameters here through example. Let's say that sender 1 sends 10 short messages to this receiver, signified by those little gray boxes there. So what's going to happen here is we're going to say, I have a threshold of 5. That threshold of 5 means that when a sender sends me more than 5 short messages, he becomes eligible to use this RDMA channel here for short messages. So we said, oh, well, you sent me 10. All right, so I'm going to allocate 12 short buffers and say, all right, next time you want to send me a short message, go ahead and use RDMA for it and use these 12 pre-allocated buffers there for you. So then let's say sender 2 comes on the scene here, and he sends 3 short messages to the receiver. Well, 3 doesn't meet the threshold of 5, so we say, nope, sorry, you're going to continue using send-receive semantics. You're not going to use RDMA semantics. Now let's say sender 3 comes on the scene, and he sends 4. Again, 4 doesn't meet the threshold of 5, so therefore he is also still relegated to send-receive semantics. Then let's say sender 4 comes on and sends a whole pile of messages. Clearly, this sender meets the threshold of 5, so we say, yes, you are blessed. We allocate a bunch more receive buffers for you, and your next short messages can use RDMA, which is faster and better. Finally, sender 5 comes on the scene here, and, well, see, it looks, sender 5 sends 6 messages, and definitely meets the threshold, but this is where the third parameter comes in here and says, you know what? I'm only going to allow 2 peers to do short eager RDMA to me. So therefore the threshold was met, but I've already met the maximum number of peers that I'm going to do for short message RDMA. So therefore sender 5 also fails the criteria and stays at send receive semantics. So let's give some names to those parameters there. The first one, there's actually 4 parameters. The first one is enable, disable, the whole scheme. use eager RDMA defaults to 1 because this is a very important latency optimization for nearest neighbor kinds of communication, such as ping pong benchmarks. And then eager RDMA threshold is the threshold, right, that we discussed on the previous slide. On the previous slide, it was 5. So once 5 short messages are received, the receiver says, yes, I bless you, and you can use these RDMA buffers. Max eager RDMA is the number of peers. On the previous slide, it was 2 that we allow. And then the eager RDMA num is the number of posted receives. In the previous slide, it was 12. Now, the long message protocol is a fairly complex protocol. We have 3 phases. The first one is where the match fragment is sent across. And once the receiver acknowledges that, yes, I have a matching MPI receive that matches the message you're trying to send me, then we allow phases 2 and 3 to go forward. Phase 2 is when the sender uses send-receive semantics to send a few more buffers to cover the latency while the receiver is starting to register the memory. Because this is an expensive operation. So let's go ahead and fill that gap by having the sender immediately start sending using pre-posted buffers immediately. And then the third phase is once the receiver has started or has completed registering some buffers for RDMA, we use RDMA for fragments for the rest of the message. And assumedly the message is long enough that the startup costs here are actually outweighed and we get the majority of the messages that gets the benefit of using RDMA. So here's the parameters that cover these kinds of things. Eager limit is the maximum size of short messages. And this is basically the size of that first fragment there. The max send size is the size of the phase 2 fragments, the green fragments in the prior slide. And then the minimum RDMA size is the offset where to start doing RDMA. So it basically covers how much the match fragment and the second set of fragments, the send fragments, are going to be used before we switch over into RDMA. And then the max RDMA size is the size of the RDMA fragments. Let's put these names onto the pictures here so you can see exactly how they map. The eager limit, again, is the size of the phase 1 frag. The max send size is the size of the phase 2 fragments. The min RDMA size is really an offset into the message that says, here's the crossover point where I start using RDMA. And then the max RDMA size is the size of the individual fragments that we RDMA over in phase 3. In version 1.2.6, we introduced a new parameter. This was not available in prior versions of the 1.2 series, called PML OB1 use early completion. And I'm diverting or digressing from my earlier rule that I'm not showing the prefix. This is technically a parameter to a different part of the system. It's not the openib BTL. It's the OB1 PML. And I'm not really going to explain what that is right now, but just suffice it to say that this is the full name of that parameter, PML OB1 use early completion. It allows Open MPI to use what we call an early completion optimization, which is good for latency. So basically when Open MPI says, oh, I have given this short message in its entirety to the networking system, Open MPI says, okay, the message is done. But it doesn't necessarily imply that the message has been transmitted or it has actually even hit the wire or anything. So before the network system has given us completion, Open MPI marks completion. And if your MPI application is dipping into the MPI library frequently, this is a good optimization to take because you know progress is going to continue to occur. If your MPI application is not dipping into the MPI library frequently, you can actually get hangs that will, basically stop progress because some other, MPI process is not dipping in, not checking for completion, and not allowing the network to continue to complete the things that MPI has already marked complete. So you can set this parameter to 0. So if you see hangs when using Open MPI 1.2 series on OpenFabrics networks, you might want to try setting this parameter to 0 and see if this lets it run to completion. There's a bunch of timeout parameters for OpenFabrics networks, and these are basically defined by the InfiniBand spec, and they've kind of been more or less adapted to the iWarp spec as well, or more specifically, they apply to iWarp networks too. The min R&R timer is receiver not ready. It's a unit given in times in units of seconds. Then the IB timeout is the transmit timeout, which is plugged into the formula, which is shown there. It's basically 4 microseconds times 2 to the timeout. and the retry count and the receiver not ready count. These are all pretty much defined by the InfiniBand spec. OpenMPI does little with them other than to pass them straight through to the Verbs API when setting up communication channels between peers. Now, freelist parameters are how OpenMPI keeps a pile of free-listed pre-registered buffers for short messages and control messages and a few other things. So there's a few parameters here that govern how many buffers OpenMPI is allowed to use. We default to -1, which is infinite, so we'll always let it grow and never bound it. But for certain applications, particularly applications that get a lot of unexpected MPI messages, you may actually need to put a cap on this and say, no, actually, we're only going to allow this many buffers to exist at any one given time. And it has an indirect relationship to the number of outstanding unexpected messages in the MPI layer. So you can cap the amount of memory that OpenMPI will use for that. This actually just recently came up on the OpenMPI list, so Google around and you'll find some references to how this is used. Then the free list, the other parameters are described here. Like I said, you can basically use this to set a maximum amount of memory that OpenMPI uses for its list of free buffers. Now here's another parameter that's not directly related to the OpenIB BTL, but it's indirectly related to it. And again, this is the full name here. I've used its own prefix. mpool RDMA cache size limit. This is the amount of memory that OpenMPI, the total amount of memory that OpenMPI will return when you call MPI alloc mem. So when you call MPI alloc mem, we'll return registered memory to you up until this value. Above this value, we'll just malloc memory and return it to you, and it won't be special at all. But when you use this parameter in conjunction with several of the other parameters that I've already listed, you can establish a maximum limit for registered memory. So you can know exactly how much registered memory each MPI process is using. And that can be useful on certain types of architectures where you're fairly limited in the amount of registered memory that you can have. So come back to the question that I asked in a previous screencast, how much registered memory is OpenMPI using? Well, it's still pretty complicated. It's the sum of several different MCA parameters. Now, on the OpenMPI FAQ page, there's an FAQ item in the Tuning OpenFabrics section that describes each of the parameters and how much they contribute and basically gives a formula for how much registered memory OpenMPI uses. So it's still pretty complicated, and I've heard of some users actually creating an Excel spreadsheet to be able to model exactly what their application is doing. Now, there's a handful of MPI layer parameters that are also useful when tuning your application that's running over OpenFabrics networks. The first one is MPI leaved pinned. And this is an optimization that I described in a prior screencast where when you call MPI send or MPI receive, we register the buffer and then we leave it registered so that the next time you call MPI send or MPI receive with that same buffer, we don't have to go through all the calisthenics of registering that memory again, because it's a fairly expensive operation. So we leave user buffers registered. Now, it's fairly problematic in certain scenarios that I describe in the other screencast, but it is extremely important for benchmarks that reuse buffers, like ping pong benchmarks. There are certain real-world applications that benefit from this as well. So if your application is sending and receiving exactly the same buffers over and over again, this parameter is important for you and you want to enable it. MPI Affinity alone, the 1.2 series has some very rudimentary controls for processor affinity. You must manually turn this guy on from 0 to 1. It defaults to 0. You can set it to 1. And this tells OpenMPI that it can assume that it's completely alone on the node where it's running. So there's no other MPI jobs running. And so what OpenMPI will do is start pinning MPI processes to processors starting with processor 0. So you can say, okay, I've got 4 MPI processes running on this host, so OpenMPI will pin them to processors 0, 1, 2, and 3. Another parameter is MPI yield when idle. We default, well, actually, it's a conditional default value for this. If OpenMPI detects that you've oversubscribed a node, we're going to set this value to 1. And if we detect that you have undersubscribed or exactly subscribed a node, meaning you're running as many MPI processes as there are processors or cores or whatever, we'll set it to 0 because it's best performance when you set it to 0 and you have enough processors for processes. But if you oversubscribe, you definitely want to set this to 1 and allow MPI processes to yield and let other processes come in and be scheduled and run. Now, a side note to this, I just want to put in a little plug for the Portable Linux Processor Affinity project. It's a sub-project of Open MPI. It's a very small library to do processor affinity. It pins process A to processor X. Now, the reason for this little project is that this has actually nothing to do with MPI. We use it in MPI, but it has no MPI-specific functionality. So it's just a standalone little thing that has nothing to do with MPI at all. The original motivation for it was that the Linux API for processor affinity has changed 3 times, and it's created a number of problems over time. So it depends on a triple of what your glibc version is, your kernel version, and what your distribution did with it, and things like that. So PLPA was created to provide a stable API. And there's a new version that was recently released that also can map socket core tuples. So it's very handy. There's actually a command line executable that you can use to say, hey, bind this process to socket 3 core 2. And PLPA does the right magic to figure out exactly which Linux virtual processor that is and does the right magic behind the scenes. So cool project. Go check it out. It can be very useful to you. As usual, we'll give you a couple of pointers here at the end of the screencast. The Open MPI FAQ has a lot of information on it. I encourage you to go have a look at it. There's a whole category on tuning, and then there's another category for OpenFabrics stuff. Please go have a look. There's a lot of good information there. That's pretty much all I wanted to say in this screencast. Hope the information was useful to you. Thanks.